The other component of this work is to try to simulate how the landscape might evolve. And this is a geological map from Gideon Mantle, who was probably one of the most famous Wealden geologists. And he produced this lovely geological map of the Weald, and it was really one of the first maps. Then we can put this into some sort of geographic reference frame and try to digitize these different contacts and produce a very simplified model of how the geology looks today, and project these contacts across the fold of the Weald to predict how these contacts change in space. And then we can use that to calculate landscape evolution. And the basis of this is this transient stream power model. So this is change in elevation divided by change in time equals the uplift. So this is the rock uplift rate minus the erosion rate, where this is K is the erodibility, so how easy the rocks are to erode. A is the upstream drainage area, so this is how much water is coming through a specific point in the landscape. And dz dx is the local slope. I wasn't sure whether to put this in, but I know that some of you are sort of physicists and things like that, so I thought this was interesting for some. So yeah, if you're not interested, don't worry about it. I made this. Did I put this video? Yeah, I made this video here with my daughter's watering can to get across this idea of differential equations. So here the water is filling up the watering can, and at some point I increase the flow of the water into the watering can, and then the water flows out more quickly, and the height of the water increases until it reaches some sort of new steady state, and everything's balanced. And then I change the flow of water, and then the water level drops back down again until some sort of new steady state is reached, and now the water level in the watering can is not going up or down. And so this is what's happening when we solve these sorts of numerical models. And so this is what the solution to this equation looks like for a single river. So this is a river profile here, plotted as a function of length along the river versus elevation. And this is the rock uplift rate, so this is how quickly rocks are being uplifted. And so initially the rock uplift rate is very low at 0.5 kilometre per million years, which is 0.5 millimetre per year. And the river stays at a steady state, it doesn't change. This is what we saw in that watering can video. But then at some point the rock uplift rate increases to some new background rock uplift rate. And so this is equivalent to me changing the rate at which the water was filling that watering can. And so initially the river is in steady state, and then there's this increase in rock uplift rate, and the river profiles change and they evolve. And we see this increase in the elevations at high elevations over time, but lower down the river basically stays at a constant elevation through time, just like in the watering can video. And so this is a very simple model that simulates how landscapes evolve. And we can use this simple model and the simple reconstruction of the geology of the Weald to try to simulate how the Wealds might evolve through time. And this is the first attempt that the first time I tried to do this. And so this scenario is basically looking at a block that's uplifting, and here the chalk is exposed, and then we start to see the exposure of the relatively soft, the weak Wealden clays, and this escarpment develops. So the escarpment develops like this, and then it migrates outwards from the crest of the anticline, and the whole area becomes very flat because the rocks are very soft, and so they're not able to support steep slopes. And then in the middle of the model, the harder sandstones of the Weald are exposed. I'll play that again. So this is so somewhere here, maybe now, yeah, so this is when we see the Weald clay exposed, and then this is the chalk retreating, and then this is the sandstones that are exposed in the core of the Weald. So obviously this needs a lot of work, but it's quite interesting that we're able to do this sort of thing. And if we can use the thermochronology to constrain these models, it'll be very exciting. What's the time? Have I got a bit more time? Okay. Is everyone okay if I keep going? It's not like students. The students have to be yeah, so this is the figure that I showed before, showing long-term trends in denudation rate or erosion rate across the Weald. And these rates are very, very low. But in the central Weald, and here as well actually, the topography is very, very steep, and this suggests that the erosion rates might be much faster. And yeah, if we think about this model, there might be places that are eroding much more quickly than other places, even though there's no change in the tectonics, right? Just because different lithologies are being exposed at different times. And of course, in the core of the Weald, the sandstones that make up things like the Hastings beds, the Tunbridge Wells sands, the Cookfield stones, these are all interbedded with thinner units of basically clays. And so the geology is very complicated. Around here, there's very complicated geology with these green sand, more erosive units that make up Leith Hill and... There's Leith Hill and what's the other one that's... A little bit. I think so. But Box Hill's chalk, isn't it? Yeah. So it's not chalk, it's the one that's slightly... yeah, so in Balcombe, we see a lot of these small landslides or landslips. And these normally only occur in places that are eroding relatively quickly. And they might be eroding quickly because the rocks are very soft, or because the slopes are very steep. And when we look at the LiDAR data from Balcombe, we can see very steep topography. So these are very deep, I wouldn't say canyons, but they're very deep valleys that you really struggle to walk along. There's a lot of small landslides, a lot of trees are falling down into the river. And there are very large clasts that are being transported by storms along the base of the river. These are very active environments, I think, that are eroding much faster than 0.02 millimeters per year. And I think this is partly because we have complex stratigraphy that's revealing different rocks with different strengths over time. So one of the things that I'm very excited about at the moment are these cambering features. So this is a unit in Derbyshire that shows this complex folding, and this folding is forming at the bottom of a river valley. And for a long time, the development of these folds has been debated, and people argue whether these form, whether they're formed during deglaciation, and whether this change in temperature that is expected at deglaciation drives a change in the rheology or how easy it is for these rocks to flow. And that produces these folds and this buckling at the bottom of the valley. Or can topographic stresses drive this deformation? So in other words, can the development of these very deep valleys that we see in places like Balcombe, can that drive stresses to force the rocks to flow and produce this sort of feature? So this is also in Derbyshire that was glaciated during the LGM, whereas down here that there weren't these large glaciers in the same way. This is a sketch showing what people think is happening. So here the clays are flowing towards the valley bottom, and the overriding limestone here is basically riding on top of that clay layer towards the valley bottom. This is an example of a sketch from Freshfields Quarry, and you can see this. So this is by Percival Allen, and you can see this lovely fold that's been identified in the clay, and this has been attributed to valley cambering. So this process of clay flowing into the valley bottom. This is another example in the Wealden clay from the Southwater brick pit, and you can see this lovely fold, and the downslope direction is shown here. And so these folds are developing as the material flows downslope, essentially. This is another sketch showing what we might expect to see. And then this is now a geological map of Balcombe. So I'm going a little bit quickly. So this is Balcombe train station, and the sort of, I don't know, orangey colour is the sandstone, and then at the bottom, this darker colour here is the clay. And here the sandstone is here, and then right in the middle of this figure, or this geological map, you can see this small island of clay. And so over time, as the landscape continues to erode, this area would get bigger as more and more of the underlying stratigraphy is revealed. And so we went here to try to see if there was any signs of valley cambering and this folding process. And really we wanted to see if there was any evidence for it happening today. This is an example of a river in Balcombe, and maybe you can make out the folds here. There's a fold here and then another one here. It's quite hard to see, and this is why I don't start my talks with pictures of this. This is another really nice example of very steeply dipping clays. This is the Wadhurst clay, so this is the clay below the Ardingly sandstone. And the Ardingly sandstone is perfectly flat. I mean, I'm sure you've seen pictures of it. But the clays can be incredibly steeply dipping. This is an example here, and you can see this folding structure here. This is quite nice. And so this is showing that these clay layers are deforming. And I don't think that these are local features associated with slumping. I think it's a much larger scale phenomenon. And so we walked all the way along this river, and these pink circles are showing the strikes and dips of the clay as we walked along the river. And I'm reasonably convinced that they look like they're orientated parallel to the direction of the bed of the river. Certainly here it looks like the river's flowing more like this, and these look like they're like this. Here, maybe like this. I don't know. Maybe it's not so clear. But yeah, this is Balcombe train station here, and this whole area has recently been stabilised because the banks were collapsing. And this is the Balcombe oil well here. So this is in an area that's potentially experiencing modern deformation due to this process. So then I put together a little numerical model to simulate this process. And what this is simulating is a valley that cuts down over time. And as it cuts down, it exposes the softer clay layers at depth. And then you see the clays deforming. And this is a lot like the sorts of models that people would have done if they work on like salt tectonics. I know that's something that lots of people in the oil industry work on. So you can see this. This is coloured based on horizontal velocities, and this is vertical velocities. And you can see this sort of area here where the rocks are really moving upwards rapidly at a rate that's much faster than the surrounding erosion rates. So maybe this is explaining why we see these apparent spatial variations in denudation maybe we actually do see spatial variations in the rates at which rocks are moving upwards, and this is due to small-scale deformation. And it also has implications for what might happen if there was a borehole here. Perhaps this is being sheared at depth, and this process isn't really being explored fully. If this process is ongoing and is not a post-glacial phenomenon, it has wide-reaching implications.